Sorry about the delay, and thank you for the introduction and the invitation to Vienna, and to the organizers for putting together this nice workshop. So today I'm going to be talking about a result I recently proved with Matteo Cozzi regarding non-local minimal surfaces that are contained in a half space. Okay, so since the introduction of non-local minimal surfaces by Caffarelli, Rock-Joffre 7, they've seen a lot of research over the past decade and a half. So there's been a particular emphasis on the regularity theory of these objects, so things like classification of cones, density estimates, the monotonicity formula, things like this. More recently, there's been some interest in existence theory through min-max methods and extending these objects to Riemannian manifolds. So today I'm going to be particularly interested in rigidity of these objects. So particularly, given, say, a set E in Rn+1 with smooth boundary, if E is a non-local minimal surface, whatever this means at this stage, that is contained in a half space, is E necessarily a half space? So half spaces are non-local minimal surfaces, so are they non-trivial non-local minimal surfaces contained in a half space? So this result was really inspired by a result in the classical case of Hoffman and Meeks in 1990, where they proved, okay, let n equals 2, so we're dealing with genuine surfaces, not hypersurfaces, and let the boundary of E be connected. If the boundary of E is a minimal surface and is contained in a half space, then E is a half space, i.e. the boundary is a plane. Okay. Now, what I wanted to emphasize about this theorem is this was really the hardest dimension to do. So when n equals 1, this is trivial because the boundary is a line, and you're done. Okay? And when n is bigger than or equal to 3, then there's a counterexample given by the catenoid, which is contained in a slab. Okay? So we really wanted to generalize this theorem to the non-local case. And our main result, in its most simplest form, says, given an open set with smooth boundary that is a non-local minimal surface, and it's contained in a half space, then it is a half space. Okay? Note, there's no restriction on the dimension, okay, unlike in the classical case. Okay? So it's purely non-local. So some literature on this. This result was already known in the case of minimizers. So by Serena, Enrico, and Joachim, proved it in 2020. Okay, so really, the important part about our theorem is it's for stationary surfaces. Okay. Another result in this direction is by Matteo and Enrico in 2020, where they showed, okay, if you have a stationary surface, an S-stationary surface, and you have bounds on both sides, then you are a half space, provided those bounds are sublinear. Okay, and they're two-sided. Okay, and another result in this direction is of Matteo, Luca, and Alberto Farina in 2021, where they say, okay, if E is a subgraph with one-sided linear growth, then E is a half space. Also in this paper, they reproved the result of Enrico, Joachim, and Serena. So I should say, the result here, where E is a minimizer, really uses the fact that it's a minimizer. So it uses a blowdown argument and a uniqueness of blowdowns to half spaces. So this is not going to work in the stationary case. So we had to really change the methodology here. Okay, so what is the game plan for today? So the first thing I want to do is I want to review the classical case. So I want to give a sketch of this result of Hoffman and Meeks because we're going to use it later. And it's also simple and it's a very nice geometric argument. Okay, and I'm also going to give some relevant literature that's going to motivate some of the ideas in the non-local case. Then I'm going to introduce the non-local mean curvature. I'm going to give the proof in the planar case because somehow this is a much simpler case. And then I'm going to try sketch the proof in general dimensions. That's the game plan. Okay, so the local case. Let's begin with an open set with C2 boundary. Some preliminaries. We can measure the perimeter, which is just the Hausdorff measure of the boundary. And we can also compute the first variation. And it's given according to this formula, where this object we call the mean curvature. So it's the sum of the principal curvatures. Okay, and then E is a minimal surface if the mean curvature vanishes everywhere. And minimal surfaces satisfy a strong maximum principle. So if E and F are sets such that the boundary of E and the boundary of F are minimal surfaces, they're connected, and then E is contained inside F, and the boundaries intersect, then we necessarily have to have that they are the same set. Okay, so I'm going to use this in the proof of the Hoffman-Meeks result. Okay, so the proof of the strong maximum principle in the half space. So we want to begin by translating and rotating our set E so that it lives in the lower half space. And by translating upwards, we can assume that the distance from E to the upper half space is 0. Okay, so we have something like let's say this for now. This is my set E. Okay? But I've already drawn a bad picture because if E touches here, by the strong maximum principle, it has to be a half space, and we get a contradiction, okay, because we assumed it wasn't a half space. So really, a better picture is something like this. Okay, where I'm getting closer and closer to the plane. Okay, and now we take a barrier, so a subgraph of the half catenoid. Okay, so we take here, and I haven't given myself loads of room, here to be the half catenoid. Okay, right? Now, by continuity, we can take our E and slide it up a little bit without intersecting the catenoid. Okay? And then we homothetically rescale the catenoid to bring the arms of the catenoid down to obtain a touching point. But then the moment we have a touching point, this contradicts the strong maximum principle. Okay? So we obtain that our initial assumption was wrong and E was a half space. So the counterexample in higher dimension was the catenoid, but then the proof in this dimension relied as well on the catenoid. Okay, so more generally, this half-space theorem was looked at in Riemannian manifolds. So Rosenberg, Schulze, and Spruck in 2013 gave the definition that a Riemannian manifold has the half-space property if every proper minimal surface in M cross R not intersecting M cross 0 is a horizontal slice. Okay. Now, I mentioned this because they prove that, okay, under uniform L infinity bounds on the sectional curvature, that if M is parabolic, then M has the half-space property. So one definition of M being parabolic is that there is no positive fundamental solution of the minus Laplace-Beltrami. Now, I mention this because this is going to give an initial motivation for the non-local case. Okay? Because particularly in Euclidean space, it's an if and only if. Okay? The Euclidean space is parabolic if and only if n is 1 or 2. Okay, so the non-local case. So we begin by giving some introductory definitions. So S is a number between 0 and 1, and it's the non-local parameter. And the S perimeter is given by this object here. Okay. So it's well known that the S perimeter interpolates between the classical perimeter and the volume. So as S goes back to 1, after renormalizing, we get the classical perimeter. And when S goes to 0, we essentially get the volume. So if E is bounded, we get the volume. Okay. And it's a non-local object because this integral is taken over all of Rn. So if I change a part very far away, it changes the entire perimeter. Okay, and then we can play the same game as before, and we can compute the first variation of the S perimeter, and we get this, where Hs is given by this integral. Okay, and we call this the S mean curvature, okay, in analogy to the classical case. Okay, and then continuing on, as in the classical case, if the S mean curvature is 0 everywhere on the boundary, it's an S minimal surface. Now, heuristically, if the S mean curvature of a set at a given point is 0, this somehow says that with respect to this weighted, with respect to this measure, the complement of E and E balance out in the entire set. Okay? So somehow being an S minimal surface says that everywhere yourself and the complement are balancing. Okay. More generally, we don't have to assume regularity on the boundary. We can talk about non-local minimal surfaces in the viscosity sense. So it's a S minimal surface in the viscosity sense if it's a super solution and a subsolution. A super solution says that, okay, every point on the boundary and every set contained inside E that touches at that point, where F is C2 in the neighborhood of E, we have the S mean curvature of F is non-negative. And vice versa, we have an analogous definition for the subsolution. Okay, so in general, so first of all, the S mean curvature satisfies comparison principles similar to what the classical curvature has. But actually, they're actually much stronger. So here, if I have a set E contained inside F, and I have a point on both of their boundaries, I can compare their curvatures, and the difference is this weighted integral. Okay? So I get this comparison between the two curvatures. Okay, and this leads to the strong maximum principle for non-local minimal surfaces. So I have a set E contained inside F. They have a point on both of their boundaries, and the curvatures have the correct signs in the viscosity sense. and some regularity, then we can argue that E actually equals F, okay? Just like in the classical case. Okay, so recall the theorem, okay? And there should be, this is a typo, and it should also be a non-local minimal surface. So let E be an open set with smooth boundary, a non-local minimal surface, and it's contained in a half space. Then we want to prove that E is a half space. So the idea is initially, like in the classical case, we want to construct a barrier that has the correct sign and run the same argument. Okay? So the question is, what should this barrier be? Well, in the classical case, it was the catenoid. And there is a catenoid in the non-local case. So a result of Davila, Del Pino, and Way proved there exists a non-local catenoid, and so the non-local catenoid is locally like the classical catenoid, but then at infinity, it grows linearly, which is actually good for us. Okay? Now, what goes wrong? So in the classical case, I actually didn't take the catenoid, I took the half catenoid. So I chopped it in half, and then I used that as my barrier. So we do this with the non-local case. We chop off the bottom, and then we consider this set. But now there's an issue, because now if I look at the S-mean curvature at a point here, say, I see a lot of the set E and not a lot of complement, and its S-mean curvature becomes negative, which is the wrong sign. So this doesn't work anymore. Okay. Now, there's a relationship between the S-mean curvature and the fractional Laplacian, very similar to the mean curvature and the classical Laplacian. So if I take my set E to be a global graph, and its gradient to be sufficiently small, then the S-mean curvature looks approximately like the fractional Laplacian of order s plus 1 on 2. Okay? Moreover, we know the fundamental solution of the fractional Laplacian, and with this parameter, it's given by this, and the C is explicit. And in fact, the C is positive if and only if s plus 1 is less than n. Okay? So if we think back to the case of the Riemannian case in the classical, we had this parabolicity somehow says the half-space property should hold. Okay? And the parabolic case is precisely the case when n equals 1 and s is between 0 and 1. So somehow this suggests in the planar case, there is a barrier, an easy barrier. And this is our first result. So we look at the planar case, and we suppose E is contained in a half space, and it has S-mean curvature less than or equal to 0 in the viscosity sense. Then E is a half space. And the idea is exactly the same as the local. Okay? So it follows by constructing the correct barrier. Now, the barrier does have to be slightly adjusted. So if I go back to here, the fundamental solution when n equals 1 should be x to the power of s. Here, well, if we take x to the power of the s, at infinity, the S-mean curvature of this goes to 0, so then we have to consider higher order terms. Okay? And it's not clear what the sign is. What's easier is we have a bit of room. So we just take x to the power of alpha instead, with alpha less than s, and at infinity, this has the correct sign. And then we run the same argument as in the classical, okay? Which gives us the theorem. Okay, so here is the general statement, the full statement of our result in any dimension. So we let E be a measurable set that's contained in a half space such that E has zero S-mean curvature in the viscosity sense. Now, we make one of two assumptions. One assumption that E has uniform thick density estimates around every point on its boundary. So in other words, given any point on the boundary of E, if I look at the volume of a ball of radius rho around that point minus E, this is bigger than or equal to some constant rho to the n plus 1. So this is like the volume of B rho. Okay? So either we make this assumption or we assume that the boundary of E is a C1 hypersurface outside of a compact set. So initially I stated it for smooth, so that falls under 2, for example. Okay, and then under these assumptions, E must be a half space. Okay, so now I'm going to sketch the proof of this. Okay. So initially we want to take the same barrier as in the planar case, so the x to the alpha with alpha less than s. Okay, this no longer has the correct sign, but we do have estimates. Okay, so that we have that if we take this barrier, then there exists some constant such that the S-mean curvature decays in this way. Okay. Now, what's the idea? The idea is twofold. So first of all, from this lemma, very far away, the S-mean curvature of F is close to 0. But small. Okay, so first of all, I want to force my E in my theorem to touch my barrier F very, very far away from 0, where the S-mean curvature of F is approximately 0. Okay? We still don't know it has the correct sign, though, the barrier. So now what we want to do is we want to take this barrier F, and we want to construct an F tilde with positive S-mean curvature. And we do this by essentially removing some mass in the region F minus E. And by removing mass from F tilde, it increases the curvature, that non-local curvature. Sorry, if I remove mass from F, this increases its curvature, its S-mean curvature. Hopefully to get it to be positive. This is the guiding principle. Okay. So the initial setup, we argue by contradiction, just as in the classical case. Without loss of generality, E is contained in the lower half space, and the distance from E to the upper half space is 0, just like before. Okay. Now, we can also assume that the boundary of E doesn't hit the boundary of the lower half space by the strong maximum principle, because if it did this, it would be a half space. Moreover, after a dilation, we can assume that the cylinder B2 times minus 2, 0 has empty intersection with E. Okay, so in other words, okay, so this is my set E, and Okay, it doesn't intersect this cylinder here. Now, we take the barrier F as before, and we homothetically rescale it, just like in the classical case, with some parameter epsilon. Moreover, we consider a sequence of our sets E with J, and as J is going to infinity, this is going to 0. So we're moving our set E upwards, but then the sequence is slowly moving downwards, okay? Then we can choose epsilon sufficiently large, first of all, that EJ is contained in F epsilon. Okay? Next, we're going to take epsilon smaller and smaller and smaller to obtain a touching point. Okay? This is like height a to the minus 1. And, okay. My barrier looks a bit like this, and okay, it's a bit wonky, but it touches at some point over here. Now, what is the reasoning for having this J here? Is the idea is as I move this down, it's going to force my touching point to get further and further away. So if you remember, I wanted my touching point to be very far away because then my barrier has S mean curvature close to 0. So I want to take this touching point and I want to essentially send it to infinity. Okay, so then we define EJ to be, okay, the infimum of epsilon such that EJ is in F epsilon. This is non-negative and it's well defined, and it goes to 0 as J goes to infinity. Okay, now we claim that there exists some J0 for which this epsilon is 0, which is going to give us a contradiction. That's step 1, the setup. Step 2, we obtain a diverging sequence of touching points. Okay, so we assume this claim is false. So this claim that there exists a point where epsilon j is 0, which tells us that epsilon j is positive for all j sufficiently large. So for each j, there exists a point pkj that's in ej minus f epsilon j minus 1 on k. So we take our barrier, we go a little bit too far. Now, since my set E is bounded from above and my barrier is going off to infinity, the intersection is some compact set. Okay? Or in other words, this sequence pkj in terms of k is bounded. So after passing to a subsequence, it converges to some pj that's in the boundary of ej and the boundary of f epsilon j. In other words, we obtain our touching point. Now, we want to show that they go off to infinity. Assume that they don't, they're bounded, then again, up to a subsequence, pj converges to some p, and we can argue that, okay, that p has to be in the boundary of E, and it has to be on the boundary of the lower half space. Okay? But this contradicts our earlier assumption, so in other words, pj is not bounded. Okay? Now we can check that necessarily the nth coordinate of Pj is less than 1 on j, and the remaining coordinates are bigger than 1. Okay, which tells us that the limit of the norm of Pj is equal to the limit of the norm of P prime j, so all of the points except for Pn plus 1, and they go off to infinity. Okay, step 3. Now we want to rule out that Ej is too flat around a touching point. Okay, so the idea now is if it's too flat, we can apply the epsilon regularity theory and conclude it's a graph with estimates, and these estimates lead to a contradiction. How do we do this? So at the touching point, we put a cone beneath our set. So here, we introduce this cone where the opening is given by a sequence Lj. Okay? And the Lj, okay, in the limit is going to 0, so it's getting wider as j is going to infinity. And there's some other technical assumptions on what the sequence Lj must do. Okay? Now the claim here then is that, okay, and then our Cj is a sector of the cone where the radius of the sector is proportional to the norm of Pj. Okay, and the claim is that this sector can't stay inside Ej. Okay, sorry, there exists some j for which this inclusion doesn't hold for j sufficiently large. So again, we suppose not. Then, up to a subsequence, the inclusion holds. If we rescale Ej according to the norm of Pj, then we can check that E tilde j, the rescaling, satisfies these bounds, which essentially is the epsilon regularity for non-local minimal surfaces, okay? Then we apply the epsilon regularity theory to obtain that these E tilde j's are a subgraph in some cylinder. Okay, and the subgraph is C1 S on 2, and we have a uniform bound on the gradient. Next, we unpack all of these transformations that we've made, and we obtain that E is a subgraph in approximately every cylinder that looks like this. Okay, I say approximately because it's not quite this, but for simplicity, let's say it's this. Now the point is, this is going to infinity, so when j is sufficiently large, these cylinders cover all of Rn plus 1. So in other words, the boundary of E is a subgraph everywhere, so it's a global graph. So we say E is a global graph of some phi. And then again, we unpack all of our transformations and our definitions, and we obtain that it's a global subgraph of phi with this estimate for phi. And you can see, by taking j to infinity, this goes to all of Rn, this goes to 0, so we obtain that phi is a constant. Okay, so we're a half space. So this is ruling out the graph-like surfaces. Okay, so what was the final step of the argument? So we've got our touching points to touch sufficiently far away. Now we wanted to find some mass to remove from our barrier to turn it from being approximately 0 S-mean curvature to positive. So in other words, we want to construct these sets dj in f epsilon j, but not in ej, and we require them to satisfy this inequality, because it's the inequality that works with respect to the comparison principle. Okay, so I'm not going to be able to go into detail about every single estimate regarding this, but what I prefer to show you is where we find the mass. Okay, so I'll simply go through the cases and draw where we find these DJs. Okay, first we look at the case where we have the density assumption. Okay. We have two scenarios. Either, so we assume, by contradiction, that, not by contradiction, we've ruled out here, we know that this claim holds. We just showed, that it does, if it doesn't hold, we get a contradiction. So that's in force. Okay. Now, from the claim, we have one of two scenarios. Either this sector here is not inside E, or it goes through the boundary. So what is the first case? This is maybe my set E. Maybe this is E as well. And it doesn't intersect this sector. Well, this is actually the easiest case, because then we simply take our set D to be a ball here. Okay? And we can check that that has the right estimate. Now, the next case is when this sector intersects the boundary. So maybe this is something like my E goes like this, and it runs through the boundary of the cone. Okay? Now, in this case, I find a point that's inside my cone and the boundary of E. So maybe something like here. Okay. And then I can pick a ball around this point minus E. And then we get the estimate because in this set, this value is bounded by Pj. So then this object is bounded by the volume of dj divided by Pj to the correct power. And then we can estimate the volume of dj because of the assumption on the density from below. Okay, so that's where the density estimate assumption comes in, on the volume of dj. The other case was the assumption that our set was a C1, had a C1 boundary outside of a compact set. Now, in this case, we do a bit of a method of moving planes type argument, except it's not a moving planes, it's an ice cream cone. So we essentially, around our cone here, take a union of many balls of some radius r. Okay. Now, this ice cream cone is expanding as r gets bigger. And we have some inclusions with the ice cream cone and r cones. Now, we use that the boundary of E is C1 to argue that when R is sufficiently small, the ice cream cone is contained inside E. Okay, so to start the method of moving planes. And then we keep taking R bigger and bigger until the ice cream cone hits the boundary of E. Okay? And it does this at, say, radius Rj, and we obtain a Qj that's on the boundary of the ice cream cone and the boundary of Ej. But now, okay, this is like our ice cream cone, like this, and it's touched at some point Qj there, and then this gives us, from the definition of the ice cream cone, a corresponding ball here, like this. And then we take our set dj to be this ball that we obtained minus the set ej. And we can check that this dj satisfies the estimates that we wanted. The final step is we take our f tilde j to be the barrier f epsilon j minus these sets dj in each case that we found. The comparison principle tells us that the curvature of f epsilon j at the touching point is the same as the curvature of, f tilde j. The curvature of f tilde j is the same as the curvature of f epsilon j at the touching point, plus this error. But by construction of the dj, these satisfied an appropriate bound. And f epsilon j is explicit, so from our estimate from before, we have a bound from there, and this is positive for j sufficiently large. Therefore, we've constructed a barrier that's got positive curvature at the touching point, which contradicts E being a viscosity solution. Okay, so this, all in all, shows that our initial claim was true, that there exists some j naught for which epsilon j naught is 0, but then this implies that we get a contradiction. Okay. So E must be a half space, and we're done. Okay. So this is getting to the end of my talk. So in conclusion, the take-home message is that if I have a non-local minimal surface, it's contained in a half space, it's either sufficiently regular or it has uniform density estimates on the complement, then E is a half space. So to finish off some open questions, it's interesting if we can relax, does the result hold if we only assume the S-mean curvature to be less than or equal to 0 in the viscosity sense? So in the planar case, we only needed this because we just used the barrier. In the general case, we needed it to be equal to 0 because we needed to use epsilon regularity. Okay, so it's interesting, can we extend it to this case? And can we relax the assumptions? So either can we drop this C1 assumption somehow, or an interesting question by itself is, do non-local minimal surfaces satisfy uniform volumetric density estimates at all scales? Okay, so this is an interesting question regardless of this theorem. And that's everything. Thank you, everyone. Sorry.